Okay, welcome everybody to today's seminar talk of the IFIMAC joint seminar series. It's a pleasure to welcome today Xiao Mi from Google Research. Xiao studied physics at Cornell in the US and then moved in 2013 to Princeton to work on his PhD together with Jason Petter on the topic on silicon quantum dots and in connection with circuit QED. He finished his PhD in 2018 and received for his PhD and the Greene as a dissertation award. So somebody might have heard his prize talk at the last APS meetings. Then after his PhD, Xiao moved to Google Research, where he is now working on the Sycamore experiment, and you see in the title that he will be talking about this 53-qubit processor. I also would like to mention that Xiao at the moment is in California, so he has quite some time delay. For him, it's very early in the morning, and I appreciated a lot that he nevertheless accepted to talk at European noon. So Xiao, thanks for accepting our invitation and welcome to our seminar. The screen is yours.
Okay, thank you, Sigmund, for the introduction, and thanks to organizers for inviting me here. So today we'll be talking about some of the recent works, experimental works that we have been doing at Google, our quantum computing group. So my internet has been a little bit shaky lately, so if at any point during the talk you find that I get choppy, please let me know, and I can kind of switch off the video and get us a bit more bandwidth. So before I start, let me just give people a quick introduction to our group in general. So we're quite a growing group by now, probably over 100 people overall, and we're, our operation is divided into 3 areas, right? So I'm located in Santa Barbara, where most of the experiments and hardware developments happen. And we also have a fairly large group in Venice, Los Angeles, where we have really good colleagues there who develop the theoretical works, for quantum algorithms or for gate calibrations or hardware developments. And then we also have a separate operation in Seattle, where we have software engineers there that work on interfacing our hardware to the Google Cloud service. So at some point in the near future, you guys could actually hook up to our hardware and start taking data using our system. So, and this is a sort of picture of our group taken maybe a year or 2 ago. So right now it's quite a bit larger than that. So the theme of my talk today is really centers around the idea of using near-term quantum computers to do some sort of computation that is hard classically, right? So, and in the spirit of this overall theme, the talk will be structured around three different points. So at the beginning, I will introduce you guys to the quantum processor that is being used by our group, the so-called Sycamore processor. And then following that, I will show how this kind of by now famous experiment where we try to craft a particular task and use Sycamore to accomplish it much faster than a classical computer. And then I will actually devote the majority of this talk to a new experiment that follows up from this from the beyond classical task, where we actually try to see whether we can do some useful physics, try to study physics phenomenon that is actually hard to compute on a classical computer, whether that's at all possible, right? So pretty much nowadays, every single experiment done our group is very collaborative in nature. It always uses the infrastructure developed by the entire team. But nevertheless, I have to kind of acknowledge quite a few people and highlight their contributions in this particular physics experiment that I'll be talking about. So on the experimental side, we have Padram, Chris, Charles, and Yuchen, who have spent quite a lot of time on the experiment. And on the theoretical side, we have Kostia, who actually came up with some of the early ideas in the experiment and have kind of provided a lot of guidance throughout the effort. And then there's Igor and Vadim, who have also been instrumental in developing a lot of theories that are used in this work. And this is also done in collaboration with NASA, where Salvatore and Jeff are kind of really experts in large-scale simulations, and they really try to look at the experiment we have done and evaluate how hard it is to simulate the particular circuits we run on a classical machine. Excuse the title. Some of the slides are kind of taken directly from the APS talk. So let me start by introducing what the Sycamore quantum processor is. So as you all probably know, that the type of qubits used by Google is really a transmon qubits. But it's the transmon qubits that have a tunable frequency. So what is a transmon? It's really at the center of it is essentially an LC oscillator that is made from a capacitor that is kind of essentially really easy to fabricate on a system, and an inductive element, which is basically a Josephson junction, or rather a squid, which is a loop of two Josephson junctions. So what these Josephson junctions do is they allow, when you pass current through it, it has the nonlinear inductance, right? That gives you a sort of a qubit potential that is different from a harmonic potential. So what that translates to in terms of energy is that you have a ladder of energy states, but they're non-evenly spaced. So they can selectively choose the ground, the first excited state, as the qubit states and address them individually. Right. So, and the idea of using two Josephson junctions that you can thread the flux through this loop, and you can tune the frequency of all these transitions. So it's very convenient to be able to do that, because oftentimes in the qubit spectrum you have a lot of defects that are that you want to avoid by tuning the frequency. The qubits are usually driven by essentially capacity to couple the system to a drive line. And there you can feed a microwave pulse through it, and that allow you to drive transition between different energy states. And this type of thing is pretty standard in superconducting qubits these days, and you can easily achieve a fidelity on in the range of 3 nines. And in terms of readout, the qubit is coupled to a very large resonator somewhere down up there. And depending on whether it's in the ground or the first excited state, it induces a different dispersive shift in the frequency of the readout resonator. So you can sort of take advantage of that and try to figure out which state it is at. And we can usually have a readout fidelity on the order of 97 or 98%. So the real innovation that I want to highlight that allow us to do a lot of the experiments in this talk is how we do 2-qubit gates. As people usually know, that this is typically the bottleneck for quantum computing architectures, right? So a lot of the qubits can do single qubit gates really well, but the 2-qubit gates are really the hard part to get it to work really well. So the approach that is used by our group in doing 2-qubit gates is try to take two transmons and then couple them through essentially another transmon, right? So imagine in the middle of this thing, there's another transmon that is very high in frequency compared to these two guys. So what it does is it mediates kind of a virtual interaction or second order interaction between the two transmons. And by tuning the frequency of this middle transmon, this coupler, you can actually change the amount of coupling rates between the left and right transmons. And you can actually completely shut it off, right? So what it allows you to do is you can swap excitations between the two qubits at a very variable rate. So on the right is essentially plotting the swap probability between the two qubits as a function of the bias voltage you put on this middle coupler, right? So you can see at some point, let's say along this stripe here, you completely turn off the coupling. And even if you park the qubit frequency right next to each other, they're not swapping anything, right? Whereas if you move to the side, left or right, the coupling is at a very high frequency, and you're swapping probabilities between the two qubits, swapping excitations at a very fast rate. So what this does allow you to do is to do very fast 2-qubit gates. And not only that, you can also imagine that you can use this thing to actually swap excitation between the 1, 1, and 2, 0 subspace. And then after it comes back, it actually accumulates a large phase. So that allow you to not only do an ISWAP type of gates, also a CZ type of gates. So it's a very versatile platform to sort of scale up into a large system. Okay, and this is just look at that a bit more in detail, right? So what we can do with the so-called GMON architecture is that with a single analog pulse, we can actually output a gate that has a very wide range of angles, right? So usually if you bring the system, the two qubits into resonance with each other, and then put a non-zero coupling between them and wait for variable duration, TP, the output unitary is always a compensation of ISWAP gate and the C phase gate, right? And what's plotted on the right is some simulation where you can see that if you change the amplitude of the coupler pulse, the Gmax, and change the pulse duration, TP, you can tune the theta, the swap angle, to a very large range, essentially going from square root ISWAP to ISWAP. And by changing the, at the same time, the conditional phase, the C phase, also goes through a very wide range. So it's not hard to imagine that by simply tuning two pulse parameters, you can actually achieve quite a wide family of the entanglement gates. So not only is this system nice in the sense that you can always turn off the two-qubit coupling, but also it's very useful in achieving, essentially a continuous set of two-qubit gates. So with the ability to tune gates, the next question I want to address is, how do we benchmark the fidelity of these gates, and how do we improve it to the threshold where we can do large-scale experiments? So over the years, one particular technology or technique that the group developed is sort of this thing called cross-entropy benchmarking. So this is you guys might be familiar with things like randomized benchmarking, which is typically used by a lot of groups, right? So usually you have gates, you try to build a Clifford circuit, then invert it at the end and see how well it returns to the ground state. And but cross-entropy benchmarking is a little bit different in the sense that you don't use Clifford gates, rather you use sort of entanglement gate that is aiming to achieve a very chaotic output amplitude wave vector. So what you do is you build a random circuit with the gates that you're interested in, and you essentially collect output probabilities for each bit string, right? So, and then you first compute that. So that's kind of shown by the blue here. This is what you would get if there's no error in the system at all. And then there's another limit where, let's imagine the system is completely broken. Then of course, it's a uniform distribution at the end of it, right? No bit string is any different from the other. It's all equal probability. So it's sort of a dashed line here. So that's the broken limit. So usually what we're getting in the lab is somewhere in between, which is this orange thing with the actual data. So it's sort of it's a distribution that resembles to some degree the ideal distribution, but it's also kind of more uniform compared to that. So there's a way to actually compute the cross entropy, which is essentially the statistical correlation between the ideal distribution and the output distribution, and that gives you a fidelity number. And what can you do with this fidelity number is actually quite amazing. So one thing that you can do is actually to help you improve the fidelity of the gate in situ. What does that mean? So let's say I have only 2 qubits, right? I want to basically improve the fidelity of the 2-qubit gate between those two guys. So what I do is essentially I run XEB just with those 2 qubits, right? And I basically, let's say I imagine this is some particular C phase gate or ISWAP gate, and I output and I compute cross entropy fidelity and sort of see how it varies with cycle number, right? How many cycles I have in the circuit. So you get a decay curve, this red curve here. Now I kind of come back and think, oh, maybe I made an error somewhere in my unitary. Maybe the gate that I'm doing is not quite what I think it is. So now what you can do is you use the exact same data and try to optimize across entropy fidelity by varying the angles within the unitary. Typically in the lab, that gives you increase or rather a decrease in the decay rate. Right? So after optimization, you get this set of blue points here, and then now you kind of know that exactly where you have made a mistake, these so-called coherent errors. So generally there, some mistake in the single qubit phases in the unitary. So you can actually go back and try to tweak your pulses to fix those errors. So it's very powerful in the sense that it not only allows you to know what the fidelity of the gate is, but also give you a way to improve it in situ quite substantially. In fact, this example, you can see that error goes from almost 1% to only 0.5%, just by doing this optimization and sort of iterative loop to feedback and fix the pulses. So this is one part actually is really useful, and it's actually what we use to bring our system to the highest fidelity it could have. The other thing, which is going to be tied to this beyond classical task I'm going to talk about next, is that XCB is a very robust fidelity estimator. What does that mean? It means that it works for figuring out the fidelity of circuits that is well beyond 2 qubits, right? So this is here is the example data from 16 qubit circuits. You might naively think, oh man, this thing actually requires to figure out the probability of every single bit string. This sampling overhead must be terrible, right? Once the Hilbert space exceeds a certain size. But it turns out that you don't actually need to estimate the entire distribution. All you need to do is to sample a collection of bit strings. And there's this uncertainty relationship there's uncertainty in fidelity estimation that actually scales as 1 over root n samples. So if your fidelity is 1%, all you need to do is to get 10,000 samples to estimate the fidelity to that precision. So so basically that means that you have, even if your Hilbert space is huge, you can actually get the idea of what the fidelity of your system is by doing a number of bit string sample that is well beyond the size, well below the size of that Hilbert space. So this is quite amazing, and allow you to basically quickly know what the fidelity of the entire system is, without having to go through the laboring pain of building Cliffords for multi-qubit circuits, which we all know that is a very painful task. Okay, and then just looking at this gives you an idea, right? What if I keep adding more qubits to the system? Fidelity will go down, but hopefully I can still resolve it within a few million samples or something like that. But as you add more qubits, the classical computation gets harder and harder, right? So maybe at some point, if I have sufficient fidelity in my system, I can sample bit strings at the fidelity that is much higher than what a reasonable amount of computation, what a reasonable computation on a classical machine could do. That's basically the underlying idea of this beyond classical task that we'll be talking about as the next step. Okay, so now let's go over this so-called quantum supremacy experiment. So what this experiment does is basically, okay, first you have to tune up the entire system. So not just 16 qubits, but the entire 53 qubit system, where there are 88 couplers in total and 53 qubits in total. So by using a combination of different techniques, including XCB, we're able to bring the fidelity of different gates in the system to, to pretty high level, all within 1%. So this is the first step towards this beyond classical task. And the second step is to define this task more carefully. So what we're going to do was we're going to build a random circuit that is basically layers of single qubit gates that are chosen at random from different rotation axes, and then layers of 2 qubit gates between all the neighbors, right? So we're going to run this quantum circuit, and then at the end of it, we're going to collect millions of bit strings, right? And but if the circuit is hard to compute classically, it's hard to know what the fidelity is, right? Because there's no point of reference. So to know that you have really truly crossed into the the beyond classical regime, what you need to do is actually have versions of the circuit where you can actually verify that what the fidelity of the system is. So what we end up doing is we run a few circuit variations. On the left is some class of so-called easy circuits where instead of doing all the gates, we actually leave out some of the gates in the application that allow you to introduce cut in this tensor network thing which we use to compute the circuits classically, make it easier to spit out answers. And in some cases, we just introduce an entire cut in the system, so we leave out these gates entirely. That also makes it easy to compute classically. So what we'll be doing is we run these circuits where we know we can actually compute answers. So we can compare the bit string we collected to the distribution that we computed and know exactly what the fidelity of the system is. After we have confidence in that number, then we run the hard circuit and collect the bit strings and essentially take that to the bank and say, oh, challenge the supercomputer, basically. So how does the result look? So this is the results of this easy circuit that I just mentioned. So what's plotted here is we fix the circuit size to a particular depth, right? A fixed number of cycles, and we gradually add more qubits into the system. And all these circles and crosses are basically the fidelity numbers that we pull out based on these different circuits that can be easily computed on a classical machine. So what's really interesting here is no matter what you're doing, the fidelity follows the exact same trajectory, right? So all these circles and crosses are basically designing the circuit in different ways. But as long as the total number of gates you have in your circuit is roughly a constant, the fidelity get is almost the same. So this gives you a tremendous confidence that if we vary the circuit to the hard circuit, which have more or less the same number of gates as these easy circuits, we will be looking at these fidelities as well, right? But the nice thing is once you have that, once you run the hard circuit, it's no longer possible, as we know, to compute what exactly the distribution is. So this is really the heart of the supremacy task, the beyond classical task, is to have a way, namely XEV, to know the fidelity of the system to very good precision, and then also have that circuit impossible to compute on a classical machine. So with that in mind, so you might ask, what's next, right? So as many of you guys are aware, the beyond classical task is sort of is a very carefully crafted task that has it has certain uses. It can be used as, for instance, a certified random number generator, but it doesn't give you a whole lot of application beyond that, right? So the focus of our group right now, at least some of us, is to try to figure out what other applications can our system have. How do we move beyond what we have already done? So one particular area that we're turning our eyes on is asking ourselves, can we use the system to do physics discoveries? Right? Can we actually study useful physical phenomena with our system? And hopefully that phenomenon is also kind of a thing that you can't really compute easily on a classical system, on a classical computer. So that's what's next. But what is really what is really the distinction between this beyond classical task and the next thing that we're going after? So the distinction lies in how how you observe, how you characterize a system. So pretty much any quantum algorithm or experiment you're going to run, is like this. You start a system on a very simple state. You run a unitary evolution of the system, and what you end up with is really a quantum universe, right? It's a sort of very complex wave vector with a very large dimension. So typically, what the beyond classical task did is actually try to sample from this large universe. You try to pull out bit strings and try to look at those bit strings and find out meanings from them. But this is not typically what we as physicists care, right? What usually as a physicist or condensed matter physicist care is you actually care about local observables. Typically, what you do is you put yourself somewhere in the universe and figure out what the overall evolution of the system does to what I'm seeing locally. That's really the spirit of a lot of the condensed matter phenomenon. So that's kind of what we're trying to move toward is try to, instead of sampling from the global state, which is very hard to interpret, we try to move toward local observations, quantum observables, right? So that's our next step. So the next thing is to ask yourself, okay, suppose we want to look at local observables, what interesting phenomenon can we study? So what we have started to, we have investigated this thing called quantum scrambling. So it's sort of a phenomenon that relates to the fact that as you evolve a system, the local information is actually gets spread into the many degrees of freedom of the entire system. Right? So this is actually a very prevalent mechanism in nature. So quantum scrambling really spans different fields. Right? In high energy physics or quantum gravity, there's something called a fast scrambling conjecture, which has to do with the fact that the black holes might be the fastest scramblers in nature. And in condensed matter, this is sort of the favorite hunting ground for AMO physicists, is to study thermalization. Right? How does the system evolve from a simple state into something that obeys the laws of quantum statistical mechanics? And then there's also kind of exotic quantum phases like many-body localization or this strange metal business in recent years. All of these phases, they somehow resist scrambling. So all of these phenomenon have the underlying mechanism is all about quantum scrambling. So it's an extremely relevant physical mechanism that we have set our eyes on to study in detail. So let's kind of look at what the meaning of scrambling is. Right? So it has a very interesting classical analogy, which is sort of in classical mechanics, that usually equations of motion have two different flavors, right? They're either integrable, where they never quite, they only sample a very select subset of the phase space, or they're non-integrable, where as time goes on, the system become increasingly unpredictable and start to sample uniformly all points on the phase space. Right? So scrambling is somewhat similar to this mechanism, and it's local observable. Its local manifestation is this so-called butterfly effect, where if you perturb the system at one point in time or in space, just a tiny bit, it manifests as a really large perturbation through the entire system at a later time. Right? So scrambling is sort of the key to studying the computation. It is also kind of incidentally the key to the computation complexity of classical dynamics. As we all know that chaotic dynamics are really hard to compute and really hard to track. Quantum mechanically, though, the scrambling mechanism is a bit different. It's actually a bit more complicated. So the closer analogy for scrambling in the quantum world is the sort of the spreading or perturbing in real space, which is called operator spreading. So how does this work? So let's imagine you have an operator, a local operator, let's say a sigma z or sigma x. As you start to evolve the system forward in time with the unitary, let's say u, then this operator becomes u dagger sigma u, right? And if your unitary is non-local, this initial operator becomes sort of mapped and start to capture all degree of freedom in the entire system. Right? It start to kind of include increasing number of qubits, sort of which is described by this Lie-Cone structure here. So this is the butterfly effect in the quantum world, which is closer to the classical analogy. But it turns out this is not the only thing that matters. There's another way where scrambling happens. Is actually in operator space. So what does that mean? So basically, I could have, you can imagine that the local operator can sort of get spread to all sites, but it could still remain a single basis operator, right? So a classical example of that is a Clifford circuit, which it keeps mapping a single operator to a different operator, although that operator can start to include more qubits. And we all know that Clifford circuits are easy to compute. So basically, operator spreading is not enough for the computation complexity of quantum dynamics. What really needs to happen in conjunction and in addition to the spreading in real space is actually the initial local operator needs to multiply itself and start to grow into exponentially many operators. This is something called operator entanglement. So basically, for scrambling to happen in the quantum world, you need to have both operator spreading in real space and operate an entanglement of operators in the space, in operator space. So in all of the past experiments for quantum scrambling, these two mechanisms have not been distinguished from each other. And this is the task we have set ourselves to do in this upcoming physics experiment, is to try to distinguish these mechanisms and see whether indeed quantum scrambling is a hard thing to compute classically. So this is the setup of the experiment. So basically what we're doing is we have a system qubits. We will start from one-dimensional case and then move on to the two-dimensional case, right? And then what we do is we evolve the system forward with a big unitary. And then afterwards, we perturb the system locally with just the sigma z flip in one of the qubits. And then afterwards, we evolve the system backward with the U dagger. This might look easy to you, but actually creating the exact reversal of the quantum evolution is quite a hard task, and took us quite a while to figure out how to do this properly. But I won't touch on the technical details of how to do this. So just take me at my word that we can actually reverse our circuit pretty precisely. Okay? So you can, if you look at this middle block, it's basically a time evolved operator of this butterfly operator. And then there's an ancilla qubit that we place outside the system that gets entangled with the system with a couple of CZ gates before and after the evolution. So what it does is it allows you to actually conveniently look at the correlator, which is called the time order correlator between the butterfly qubit, the butterfly operator, the O, right here, and the sort of the sigma z operator, the measurement operator at the measurement qubit site. So it's sort of a 4-point correlation that is sort of applied opposite in time, hence the name. This is fairly mathematical, but its meaning will become clear in a second. Okay. So basically, this setup allows us to basically look at the OTOC between the measurement qubit and the butterfly qubit. So this is the first experiment we're going to do. It's going to be one-dimensional. It's going to be in 1D, and the random circuit, the U, is going to be a circuit that's composed of random single qubit rotations along any of these 8 random axes and a layer of ISWAP gates. Right? And then this is the data that came out of it. So what is sort of measured at the end of the circuit is really just the projection of the ancilla qubit to the y-axis. So it's truly a local observation. So you don't look at the global observable of the entire system this time. You really just look at the observable at one particular location in your system, right? And then this color curves is what happens to this projection as you apply the butterfly operator further and further away from the observing point. So what you see that as you go along this chain and move the butterfly operation away from the observer, it takes longer and longer for the observation for the local observables, the sigma y, to decay down, right? So that's kind of shown by this color curve here. But the problem with this data set is on top of this trajectory, there's an overall decay attenuation of this local observable. This is not surprising because it's a very long circuit, and roughly speaking, the local observable in the system decays as overall circuit fidelity. So by the time you have gone really deep and have applied a few hundred gates, you only end up with 1% circuit fidelity. So it looks sort of miserable because everything is kind of decaying out. So the power of the nice thing about this experiment is there's actually a way to remove this decoherency effects. So in addition to all these color curves, we also measure the observation of projection without applying the butterfly operator. And that's shown by this gray thing, this gray line on top of all these family of curves, right? So ideally, this should be just one, right? Because without this perturbation, everything reverses itself exactly. So you shouldn't have decay. But in presence noise, this thing decays. But you see that the envelope of this thing is exactly like all of these other curves with the butterfly operator applied. So what you do is you now divide out all of these curves with this reference curve, which we call the normalization curve. And this is what you get. So now it looks like a very nice picture, right? So the OTOC, which is actually has to do with the commutator between the commutation relationship between the measurement qubit and the butterfly qubit, have this ballistic shape, right? Before there's sufficient time to allow the perturbation at this point to travel to the observing point, the commutator between the observer observer and the butterfly remains unity. So the OTOC remains at 1. But as soon as you have this thing, the perturbation has reached the observing point, these two qubits becoming entangled, you see that the commutator drops to a negative value and then rapidly goes, converges to 0. So by the way, this is all taken taken as average signal of a collection of different circuit instances. Later on, we'll actually investigate what happens if you look at individual circuits. Right? So right now, it's basically an average signal from a lot of circuits. But even from the average signal, you can see a clear picture of entanglement spreading. Sorry, you can see the clear picture of operator spreading through the system. And then you can do the same thing basically in 2D and look at what happens with the circuit. So this is a 2D map of the OTOC value at different times, right? So when the circuit depth is shallow, the observer has only been entangled with other qubits, so you only see a few drop-off in OTOC values. But as soon as you kind of have deep enough circuits, this observer is entangled with everything in the entire system. Or in other words, the butterfly operator has spread through the entire system. Then you see that OTOC essentially dropped to 0 for every single site. And up to 15 cycles, we see that the original perturbation has spread through the entire system. Right? Also interesting is that this is ISWAP gate, and we see that the propagation is essentially ballistic. Right? The boundary between where the light cone is, it's very sharp. It turns out this is actually a special property of the ISWAP gate. For more generic circuit, the spread is actually diffusive in nature, and we see that in our experiment as well. So what we do is we change the entangling gate from the ISWAP gate to the square root of ISWAP gate, right? So this is actually mimics a more generic circuit where ISWAP is sort of a special gate that has maximal entanglement properties. But square root of ISWAP is somewhere in between. So now you see that the spreading is more diffusive in nature, that it's kind of slower. At the same time, the boundary between where it's entangled and where it's not entangled is not sharp anymore. Yeah, so it's kind of an interesting phenomenon to see in our system. Well, all this is nice and good. We do realize that this is essentially just looking at operator spreading, and it has a nice classical distribution. You can actually map this quantum process to a classical Monte Carlo process, or what's called a population dynamics a process. So, and they allow you to basically easily simulate the trajectory of the OTOCs, right? So this is, these solid points are the data, and the dashed lines are actually what you get out of the classical simulation. As you can see, that the agreement is quite good. So while this is really nice as a benchmark of how well your system is working, it also is kind of sad because this is essentially a classical phenomenon. So as I've alluded in the beginning, for quantum scrambling to be truly complex and truly difficult to study classically and worthy of our time on a quantum machine, we really have to look at the operator entanglement aspect of it. So how do we resolve operator entanglement? It actually requires us to look at a different thing about OTOC. So up to this point, I've shown you only the average value of OTOCs across a family of circuit instances. So there you see a sharp drop off in its value as soon as two qubits get entangled, right? So that's kind of these solid big purple dots here. But what you kind of notice is, what if I start to look at individual circuit instances, right? Instead of averaging over circuits, I just look at one instance and then another instance. So these kind of light purple lines are what happens if you just look at individual circuit instances. Right off the bat, you notice they're quite different, right? While while there's a sharp drop off in OTOC values on average, individually they fluctuate quite a bit. Sometimes even quite a few depths after the light cone has reached the observation point, you still have fluctuations in OTOC value for some instances. Right? It's only quite a few depths later, everything converges to 0. So it turns out the fluctuation of the OTOC values is the key to resolving operator entanglement. So this is the thing that we can now start to measure our system and see how it relates to operator entanglement. So how we do that in practice, so we also need to design our circuit a bit differently. Right? So now what we're going to do is we're going to fix our cycle to, let's say, 12 here. 12 circuit cycles. And we start to play around with the composition of gates in our circuits. So prior to this, we have applied any random gates from this 9 different choices. But it turns out that for these 9 gates, 5 of them are Clifford gates, and the other 4 are non-Clifford gates. Right? So the Clifford gates are basically the I swap and any of these rotations along the cardinal axis, X or Y rotations. Whereas the non-Clifford gates are any of these pi/2 rotations around an axis that is not X or Y. Yeah. So why do we classify them this way? It's because that the Clifford gates and non-Clifford gates have very different impact on how how an operator evolves in time. So this is an example sort of trajectory of how a polystring or product of operators evolve, right? So at the beginning, your butterfly operator is just a single poly operator at one particular location in space. So you can see that if you fire up Clifford fire Cliffords at this particular operator, it can sort of start to spread to other sites, but it never multiplies itself. A single operator remains a single operator or polystring. But as soon as you start to apply non-Clifford gates like these Y or B or W's, these polystrings start to become a superposition of different polystrings. Right? It starts to become 2 of them, and then 6 of them. And you can imagine as you have more of these, there's essentially an exponential growth in the number of polystrings that make up the original butterfly operator. So basically, what you can do is by tuning the number of non-Clifford gates in your circuit, you can control the degree of operator entanglement that is sort of engendered by your circuit. But you can sort of, but the Clifford, especially the ISOP, control the degree of operator spreading. So by changing these gate compositions, you can tune these 2 different mechanisms independently. Okay. So what we now do is we basically look at what the OTOC values are for individual circuits when the number of non-Clifford gates in the circuit start changing, right? So when the number of non-Clifford gates is ND equals to 0, it's basically a Clifford circuit. So at the output of the system is still a single polystring. So what it does is the OTOC value essentially fluctuate between plus and minus ones. And this is basically what we see in data, right? This is data. You see that the OTOC basically centers around 0, but it fluctuates hugely between plus and minus ones. Now, as you start to increase the number of non-Clifford, you notice that everything started to drop towards 0, namely the fluctuation of the OTOC values across circuit instances started to decrease. This is sort of manifestation that you're having more and more operator entanglement in your system. By the time you have reached 32 non-Clifford, you have so many non-Clifford, you have so many polystrings at the end of it that they all average out to 0, right? So essentially, by tuning this knob, this ND, you're turning up the heat. You're allowing your system to thermalize, right? So just to see how this translates to operator entanglement and operator spreading, you can see the average OTOC value throughout this entire trajectory plotted on this, here, is essentially 0 all the way. The average value is always 0. So the operator spreading is exactly the same. Whereas the operator entanglement, sort of shown by the OTOC fluctuation, has a sort of exponential-like decrease as you increase the number of non-Clifford gates. And this is also related to the fact that the number of polystrings at the output of the circuit, MP, is growing exponentially, right? So now we have been able to basically independently tune the degree of the two scrambling mechanisms and also resolve their respective signatures. You might ask yourself, okay, is there any chance we can study something hard, from an operator entanglement perspective? It turns out it's a very promising thing to do, because if I simulate these exact OTOC values, hand it to NASA and they use tensor contraction to figure out what the ideal values are, you agree amazingly well with the experiment, right? You see, these dashed lines are the simulated results. There's virtually, pretty good agreement. And it's also amazing to think that this comes out of a 53-qubit system with hundreds of gates. And the overall fidelity of the circuit is only 6% where we did it. But somehow this local observation after all this normalization procedure is agreeing almost perfectly with simulation. So this gives you an idea that, oh, maybe I can do something hard with it. Right? So just to give you an idea, you can sort of define a signal to noise ratio and translate that to a fidelity of the local observation. It's 10 times higher than what the actual circuit fidelity is. So now let's look at how hard it is to actually simulate this particular experiment. This is a simulation time estimate that our collaborator has produced for us. It turns out as soon as the system exceeds 400 ISWAP gates, it's actually almost impossible to simulate that, at least under any known sort of algorithms. So you can sort of set a boundary here and say, if our system has more than 400 ISWAP gates, it's hard to even simulate a single OTOC value on a supercomputer. That sounds really promising. But let's see how we're doing experiments, right? So we start to walk up this little ladder here. So basically, we started to increase the circuit depth and putting more and more entangling gates in our system, and start to look at the OTOC values and compare that with simulation. So it's easy to see that when the number of gates is small, you have really good agreement between simulation and data. But as you kind of go across 250 gates or so, the agreement start to kind of pull apart, right? And essentially the OTOC fidelity, the measurement fidelity start to decrease. So it's not hard to imagine also that the agreement will be very poor once you have reached this point. So at this point, we don't have enough precision in our system to cross comfortably into the hard regime. But it's also kind of interesting to ask yourself, okay, can we at least predict like how much fidelity we need in our system in order to cross into this regime? So apparently that's also an impossible question to answer, because notice that as you increase the system size, the amount of gates in the system, the OTOC signals start to decrease quite a bit, right? So here, down here, you have, sometimes it goes to close to 1, whereas here, everything is attenuated to well below, 0.1. So that's kind of because, as you have more and more entanglement in the system due to the increasing number of ISWAP gates, there's increasingly more in operator entanglement. So the OTOC fluctuation start to decrease and makes everything hard to see. So in order to predict whether we can cross over this threshold, you actually need to know exactly what the OTOC fluctuation in this regime is. But that's hard to compute to start with because you don't really know what it's doing. And there's no theory available to know what really happens to this regime. So we're actually in some sense at an interesting juncture for using quantum computers because we were sort of neck and neck, right? Right now, we don't have precision to claim that we can study quantum scrambling beyond the capability, beyond the classical capabilities. But at the same time, we're not that far. Right? The classical machine could also not do much better than what we have already done. So that's a very encouraging thought that we're really exiting the age of doing simple physics demonstrations with quantum processors and actually studying hard problems that are kind of neck and neck with what we can do with theory or simulation. Right? So before I kind of conclude, I want to just give a hint at the future. So this is quantum scrambling. It's not the only thing that we're studying. It turns out because of the versatility of our processors, we can realize all sorts of gates, right? C-phase, ISWAP, or any sort of hybrid gates. So that allows us to actually simulate different physical models in our system. It goes from IC model, classical IC models to transverse IC models to more generic Heisenberg models. All of these spin models can be easily simulated on our system. And that allows us to look at really interesting physical phenomena in all of them. And just to give you an example, right, this is actually looking at XY model. So as you know that XY model is integrable in one-dimensional space, whereas in 2D is kind of a much richer problem, and it's generally a non-integrable circuit. And you can resolve that using OTOC, for instance. So here you can see that this is average OTOC values as a function of circuit depth. If you do it in one-dimensional space, the OTOC converges to non-zero values at large time scales. Whereas if you just turn the chain around and make the ladder, the OTOC value is all asymptote to 0. So it's sort of an indication that you're transitioning from integral system to the non-integral system. So this is just one of the examples where we kind of actually using our quantum system to study interesting physical phenomena. I think with that, I think I'll just conclude. So what I have shown you is that we're at an exciting time for quantum computers. Right? Our system can actually do better than a supercomputer in certain very specialized tasks. And even in the areas where we are simulating interesting condensed matter problems, we're neck and neck, right? We're not quite there in the sense that we can do better than the classical supercomputer, but we're kind of neck and neck there. And all of this would not have been possible without error mitigation, right? So this is kind of a sort of reiteration of this idea that if you're careful with how you process your signal, you can achieve much better fidelity in local observables compared to the overall fidelity of the entire system. So down here is what the actual circuit fidelity is when we're doing experiment. It drops off very sharply as you increase the number of 2-qubit gates in the system down to 1%. But with all these error mitigations techniques, we were able to push our the fidelity of our quantum observables to much higher levels. So that's very encouraging. And it takes us creativity, but it's kind of also give you a sense that we can potentially increase this even further by engineering different error mitigations techniques. I think that with that, I'll just conclude my talk and I'll take any questions.
Okay, Xiao, thanks a lot for this interesting insight to one of the most exciting solid-state quantum computation experiments that we see these days. And you already gave the keyword questions, so the talk is open for questions. Please unmute yourself if you have a question. So, well, let me just start. You talked a lot about these butterfly operations. What are suitable butterflies? Are they unitary, close to unity, or?
Yeah, so
select them?
It can be really anything, but usually we just make it a Poly operator, let's say X gate, basically.
So it need not be close to unity.
Yeah, what's really complex is this unitary. That's where the complexity goes in. It's usually a many-body circuit, but then the local butterfly operator is generally just a pi rotation, something like that. Yeah.
And related to that, the results you showed us are generic. So whatever butterfly you use, you will get qualitatively the same.
Yeah, this is very generic. So if you choose you can make this anything you want, and the measurement will basically give you the commutator like this, or the coordinator like this, right? So these O and M are basically generic operators.
So more questions. Well, I would have one on, more on the experimental side. You mentioned that it's just on this slide that it's not easy to invert the unitary operation.
Yeah.
Why? I mean, theoretically, this is actually something that we know from the Loschmidt echo in quantum chaos. But why is it? I mean, for theorists, it's relatively simple. Why is it so difficult for experimentals?
Yeah. Well, so basically, our gates are it's very hard to make a very pure I-swap case or squared I-swap case in our system because of the conditional phase, right? So so what you usually get is an I-swap gate, but it has a tiny C phase component. So the swap component you can invert by essentially sandwiching that between some local Z operations, but the C phase cannot be inverted. So that actually requires a lot more. So basically, that C phase, that parasitic C phase is the root of our problem. It's very hard to get that thing to cancel out in the U and the U dagger.
Okay, so now more questions. If this is not the case, we close the official part. Thanks again, Xiao, for accepting to speak in the middle of the night. And for those who would like to stay for some moments to chat with Xiao, they are welcome to do so. But the official part is now closed.